In this video, I will discuss the system design of Zoom or any other audio video call app. We'll see how one-to-one and group call works, what type of protocol should we use for this type of app and why. We'll see how audio video call works with or without screen share. We'll see how we record the call and few other meeting related CRUD operations. How do we create the meetings and all these things. And lastly, how do we scale this type of system? So these are the main functional requirements of Zoom. So first one is one-to-one call, then group call or conference, then audio, video or screen share. So for any type of call, whether it is a one-to-one call or group call, it can be either audio call, video call, or also we can share the screen. Then create a meeting. So anyone can create a meeting. So that person will be the host of that meeting. Then starting and ending a meeting. The host or any other participants can start the meeting and also can end the meeting. Joining or leaving a meeting. So any participants can join or leave the meeting when the meeting is still going on. So if a person is leaving the meeting, that means that only that participant will leave the meeting, but the meeting is still going on. Then call recording. So of course we can record the call and later we can refer to that. And next the fetch meeting details and all. There will be other CRUD operations on the meetings. So there are few out of scope requirements like chat. So this is optional for our discussion here, because I have also created one WhatsApp system design video earlier. So there we have talked a lot about how the chat works. So we'll not discuss it here. Next, mute or unmute. So the participants can mute themselves and or unmute themselves. Invite people, managing the participants, raising a hand. So we all know these operations if you have used Zoom, right? But these are lower priority items. We will not be talking here. So our main priority will be this portion. Next, non-functional requirement, which are the qualities of the system. So the first and the main requirement we have is low latency or real-time calls, right? And then we have high availability of the system. Data loss is okay. So in the WhatsApp system design, we have seen that we need to have guaranteed delivery. We can't lose messages. So we need a reliable connections. But here in this design, for any type of audio video calls with or without screen share, if we lose few frames here and there, that should be fine. Next, secure communications. So data loss is fine, but our calls should be very secure. So we need to have encryption and proper authentications for this calls. Then resilient to network drop. So any kind of network bandwidth change and all, so our system should be resilient to that. Users connecting from different devices using different network bandwidth, so our system should consider all these things. Next, quickly have a rough scale estimation here. Consider there are 100 million daily active users and average call takes around 30 minutes. Also consider 1 hour video is approximately 200 megabyte. And each user on an average per day is having 2 calls. So 100 million daily active users, 2 calls per day, and each call 30 minutes. That means 100 million users and 1 hour calls per day. So which means 100 million hours of data transmission per day. It can be either audio, video or screen share. So now one thing I want to mention here, whether it is a audio, video or screen share call, basically you are sending a stream of data, right? And also if it is a video call and with or without screen share, so video and screen share both are basically video streams, right? Just the source is different. For video it's coming from the camera, for screen share it's coming from the screen captures. So for video calls also we can have screen or screen share,
and for audio calls also we can have screen shares. So just the sources are different. Now here 100 million hours of data transmission per day, right? And 1 hour video is around 200 megabyte, so that means 100 million into 200 megabyte, which is 220 petabyte. In the worst case, let's say all the meetings are recorded in one day, so 20 petabytes of data is recorded per day. And let's say if we are storing it for 3 months, so that means 20 petabyte into 30 into 3, that is 1800 petabyte. If we by default we store it for 3 months. Next, network bandwidth. So 20 petabyte of data transmission per day, right? And we are having 86400 per second in a day. And if we approximate it to 10 power 5 second in a day, that means 20 petabyte divided by 10 power 5, which is 20 into 20 petabyte is 20 into 10 power 12 divided by 10 power 5 is, that is 20 into 10 power 7 bytes per second, which is 200 megabyte per second. So that is the bandwidth requirement we need. Now quickly discuss few major CRUD APIs in the system. So our main focus in this discussion will be about the calls, audio video calls with or without screen share. But before going there, I'll just quickly discuss about this few APIs. For creating a meeting, we'll have a post slash meetings API. So this is of course a HTTP REST API, and it will take subject, participant list, schedule that time, and the duration of the meeting. Now who will be the host of this meeting? The person who is creating the meeting, right? So user details we send in header using JWT token or session token, and from that we can get the host ID. For getting a meeting details, it will be get slash meetings with the meeting ID. For starting or ending a meeting, we can have post call with slash meetings slash meeting ID and start or end. Then listing meetings for a user for a day or let's say week. So consider for a day only, get slash meetings with the query param date. If the user wants to see the list of meetings for some other user, then that will be get slash meetings with the date and the user ID. So of course we need proper authorization, role based authorization for this APIs. Next, for cancelling or deleting a meeting, it will be delete slash meetings with the meeting ID. For joining a meeting, it can be a post slash meetings, meeting ID slash join. For listing the participant, it can be get slash meetings with the meeting ID slash participants. It will return the list of participants for the meeting. Now let's come back to our main part, that is the calls, right? So which protocol we should use for the calls? Our known way of communication, we know about HTTP, HTTPS, also we know about the WebSocket. So both of these are TCP based. So TCP is a transport layer protocol. So consider this HTTP or HTTPS. So this is from client to server, and for WebSocket, this is a bi-directional connection. Both client and server can send messages to each other. But both of these are TCP based protocol. Now let's talk about the TCP a little bit. So TCP is a connection oriented protocol. So let's say this is the client and this is the server. To transfer data between client and server, first we have to establish a connection, and that happens via this three-way handshake. So client sends one sync call, server acknowledges that, and then client sends one acknowledgement of this server acknowledgement. And with this three-way handshake, the connection is established, and then sender and receiver can transfer data. It's a reliable delivery protocol. So the transfer happens via small data packets, and each packet will have a sequence number. So if one data packet gets lost, the sender will retry to send that again. It's ordered data transfer protocol. So this receiver is receiving the data packets, right? So it can happen that the receiver is not receiving the data packets in order, right? Few data packets can get lost, so it will be retried again, right? So it will not come in order in that case. Even because of some network condition, the data packets might arrive in not in order, right? So then in the receiver side, based on the sequence number, the data packets will be arranged. Next, flow control and congestion control. Flow control is based on the receiver's bandwidth and all, sender will decide the flow of data. Congestion control is based on the network bandwidth and all, uh, sender will decide the flow of the data. Next, talk about UDP. This is also a transport layer level protocol. This is connectionless. We don't need to establish a connection before to send the data packets. So let's say this is the sender and this is the receiver. So the sender needs to know the receiver's address, the public IP address, and sender can directly send the data packets there. So it's unreliable delivery. So let's see here, this packet is delivered, but this is getting lost. So here sender will not retry again. Unordered data transfer. So because of network conditions and all, the data packets might arrive not in order. No flow control and congestion control for UDP. But the UDP is faster than TCP. So for our solution, do we need reliable delivery? It's okay, right? If we lose few friends. So for our use case of video audio calls, we'll be using UDP because we don't need extra handshake, reliability, ordering of data packets and retrying lost packets, right? But for everything else, we'll have TCP. Now here is a quick recap of WhatsApp system design. So if you have seen my WhatsApp system design video, you will remember that if user A wants to send message to user B, the message will be transferred to this WebSocket handler. WebSocket handler, then it will send it to this user B. So this communication is happening via this server. So, but for in our case, for the calls, the data streams, should it be transferred via server? So first user A will send it to server, then server will send it to the user. It's better if we have a peer-to-peer connection, right? So the client user A can directly send the data to user B. So that is called peer-to-peer connections. Now for peer-to-peer UDP connection, sender needs to know the public IP address of the receiver. Then only sender will be able to send the frames there, right? So here how A and B will know each other's public IP address. Before that, how they will know their own public IP address? Because users will be connected to a local network first, right? And they will have their own private address, but they need to know the public IP address to send the data frames. So let's quickly see here how these public and private IPs are connected. So let's say these are the users in the local network and these are the private IP address, and this is the router plus NAT layer. So router NAT is network address translation layer, and this has IP address 1234, let's say. So this users, let's say, connected here in different ports, right? So the public IP address of these users will be something like that: 1234 P1, 1234 P2, 1234 P3. So this is just to have one assumption. Now let's see this diagram here. So there is this user A and user B, and there is this WebSocket handler via which they will communicate their public IP address. And how they will know their public IP address? From this connector. So let's say user A is connecting to this connector and got user A's public IP address, right? And user A will send the public IP address to WebSocket handler. WebSocket handler will send it to user B. Similarly, user B's public IP address will be communicated via this path. Other informations like bandwidth, device info, codec support, resolution, etc. also will be transferred, because these two clients, they need not be having the same network bandwidth. Also, they might be using different types of device. Codec support might be different, resolution might be different, right? So they need to communicate this informations, so that using that information we can come up with a decision like what quality of video frames or audio frames to be transferred. Also, cryptographic keys for encryption decryptions can be transferred so that the data remains secure. So that was one of our major requirements, that data loss is fine, but the call should be, data frames transfer should be very secure. The call itself should be very secure, right? So for that we need to transfer this encryption decryption keys, and that also can be transferred via this WebSocket handler. All this happens over a protocol named STP, or Session Description Protocol. So this communication I am talking about via WebSocket handler. Now, stream of packets transferred from peer to peer for audio, video or screen share. Now, when we are in a call, we can see what the other person is sharing, and also we can see what we are sharing, right? So each client sends one stream and receives one stream, right? So based on the UI design, we can render the incoming and outgoing streams in different or appropriate positions. Now what happens if user A and B are geographically apart, very far? In that case, peer-to-peer connection will not be that helpful, right? So in that case, we will be using a media server. So user A will send the data frames to this media server. Media server is responsible to send it to the user B or the receiver. Now all this we have discussed here, this is called WebRTC or Web Real-Time Communication Protocol. So this WebSocket handler we discussed, this is called signaling server. This connector is called stun server. The media server is called turn. So we are using this WebRTC protocol. Next we'll discuss about the group call. So we have discussed about one-to-one call with peer-to-peer connection and also via media server. So let's try to use peer-to-peer connection for group call. So there are 4 user clients A, B, C, D. Let's say there are n clients. So each client has to send and receive data frame from the rest of the n-1 clients, right? Each client has to send data to rest of the n-1 clients and also has to receive from n-1 clients. So this is called mesh topology. So I have drawn it separately here. So let's say A is sending this red streams to the rest of the 3 clients. B is sending this blue streams, C is sending this yellow or orange streams, and D is sending this green streams. So for smaller groups, this peer-to-peer connection is fine, but for larger groups, we need to have a connection via media server. So let's see here. So we are having this media server. Each client is sending just their own stream, and media server is consolidating that and sending the consolidated data streams to the clients. Now, what do you mean by large groups here? So this can be configurable, like if the number of participants in a call goes beyond that, then we'll go for this media server based approach. Also, we have earlier also have seen that if participants are close by, then peer-to-peer still will work. But if they are in different geographical location, then it's better to use a media server. Now here I have quickly drawn the high level design. So this is the meeting service. This is responsible for all the CRUD operations like creating a meeting, joining a meeting, leaving a meeting, ending a meeting, listing the participants and all these stuffs. It's using this meeting database. This can be either a SQL database or a DynamoDB. Next we have this connector service. This is responsible to provide the public IP address for any client. Then we have this WebSocket handler and then this signaling service, this layer. So this is responsible for communicating the public IP address and few other informations like network bandwidth, device info, resolution, and cryptographic keys and all. Now, different clients can be connected to different WebSocket handlers here, right? So to have that mapping, we are using this WebSocket manager. So WebSocket handler can connect to this WebSocket manager. WebSocket manager will store this mapping in Redis. And we have here the media server. So if the call is happening via media server, so this will happen via this server. Now we have this load balancer layer here. So I have drawn it like a load balancer layer, but for each different services we can have separate load balancers. Next, quickly talk about the video recordings. How would the recording work if we are using a peer-to-peer connection? It is difficult, right? So we can use media server if we want to record the call. And another way can be we can have a hybrid approach, right? We can use peer-to-peer connection for call, and parallelly we can send the frames to the server. So I have updated the design here. So after media server we have this recording service. This is collecting the data streams and writing it in this distributed file system. There will be one file creator service that is responsible for reading from this distributed file system. It will create the file and it will store it in cloud, let's say in S3. Now, when the recording file will be created? After the call has ended, right? So, this meeting service is responsible for all the CRUD operations. So, when the meeting service will end, we need to know, the file creator service needs to know when the meeting is ending. So, all the meeting related events we can write in Kafka. So, all the meeting updates, events we are writing in Kafka in some topic. So file creator service can listen to the updates, and if it is a meeting ending events, then it will read from this distributed file system, will create the file and store it in cloud. Our next topic is transcoding. So why we need that? Because different clients can be using different network bandwidth, different device type, different codec type, different resolution, etc. Right? So we need to have different transcoding for the data frames, video frames or audio frames. So for that we have introduced one transcoding service. So media service is talking to this transcoding service to create different transcoding. So based on the client's requirements, different transcoded frames will be returned. Now with this we have covered our functional requirements. Now let's see how we'll scale the services. So these services can be scaled horizontally. So if you are using a cloud solution, we can auto scale them. Let's talk about the media server, how we will scale that. So our clients can be in different geographical locations, right? So we will have our media servers also in different data centers spread geographically. So that's why we have introduced one media server broker. So media server broker can assign media servers to different meetings or different clients based on some logic like geographical proximity to clients. So one meeting could span multiple media servers as well. So let's say one meeting is having lots of participants and few are in India and few are in US. So they will connect to different media servers. So we have covered our functional and non-functional requirements. So we are done with the system design discussion here.